Hello, welcome to lesson 17. In this lesson, we are going to look at the reflecting astronomical telescope. The objective of a reflecting astronomical telescope consists of a concave mirror with a long focal length. Let's look at the types of reflecting telescopes. We need to know that there are mainly three types of reflector telescopes. That is, we have what we call the Cassegrain reflector telescope, the Newton reflector telescope, and the Claude reflector telescope. Let's begin by looking at the Cassegrain reflector telescope in normal adjustment. So here the objective is a reflecting, the objective of this reflector, the Cassegrain reflector telescope in normal adjustment, is a concave mirror with a long focal length, and light rays of a distant object are first reflected by the concave mirror and then by a small convex mirror, and the final image is formed at the pole of the concave mirror, at a hole which is situated at the pole of the concave mirror. And at that point where the image is formed, that point I where the image is formed, is also going to be the same. It's also going to be coinciding with the principal focus of the eyepiece. Let's see what I'm trying to talk about. So we have rays from infinity, that is from a distant object, reflected by the concave mirror, then by the convex mirror, and then the image is formed at the point I, which is at the pole of the concave mirror. But that point I is also coinciding with the principal focus of the eyepiece. Now we need to note something. First of all, we need to note that the angular magnification of the magnifying power of this telescope is given by f0 over fe, and which is the same as v over u, where v over u is actually the linear magnification of the curved mirrors of this mirror and that mirror. And then also f0 and fe. F0 is the focal length of the objective lens, and fe is the focal length of the eyepiece lens. Then you also need to note that this telescope, when you look at this telescope, the Cassegrain reflecting telescope, in the absence of the convex mirror, this convex mirror, the rays would actually be formed. The first image, the intermediate image, would be formed at this point, and this point would be the principal focus of the concave mirror. That would be the principal focus of the concave mirror, because you remember that when the rays are from a distant object, the image is always formed at the principal focus of the concave mirror. So that would be the principal focus of the concave mirror. So this would be a point f0, and the distance from here up to here would be the focal length of this concave mirror. Let's also look at the Newton reflector telescope. So here, the objective is also a concave mirror of a long focal length, and then light from distant objects is first focused at the concave mirror, then onto a slanting small plane mirror, and then finally the image is formed at a certain point I, which I is actually at the principal focus of the eyepiece. So that real image is formed at a certain point I, and that I also coincides with the principal focus of the eyepiece. Let's see exactly that, and we are seeing that the image is then going to be a magnified virtual image formed at infinity. So for all these telescopes in normal adjustment, we shall realize that that is the reflector telescopes. We shall realize that the images are always magnified, virtual, and are formed at infinity. Let's see this. So light rays from a distant object focuses on the objective, which is a concave mirror, onto the slanting plane mirror, and then the image is formed at I. A real image is formed at I, which is at the principal focus of the eyepiece, which thus forms a final image, which is real, which is virtual, magnified, and at infinity. Let's look at the cloud reflector telescope in normal adjustment. So here also this consists of a concave mirror as the objective, and then that concave mirror is of a long focal length. Then light from distant objects first reflected by the concave mirror, then a small convex mirror, and then onto a small slanting plane mirror, and then a final image is formed at a certain point I, which is straightened exactly at the principal focus of the eyepiece, which thus forms a final image which is magnified, virtual, and at infinity. Let's see the ray diagram here. Light rays from infinity onto the objective, which is a concave mirror, onto a convex mirror, onto a plane mirror, a slanting plane mirror, and then the final image is real, and it is formed at a certain point I, which is straightened at the principal focus of this eyepiece. So this is the ray diagram for that setup for the cloud reflector telescope in normal adjustment. Let's look at the advantages and disadvantages of these reflecting telescopes. Let's begin by looking at the advantages. One, we need to know that these reflector telescopes, in these reflector telescopes, there is no chromatic aberration, since no reflection occurs at the objective. And then also there is no spherical aberration, especially when we have used when we have used a parabolic mirror instead of the concave mirror. So since usually a parabolic mirror is used, there is no spherical aberration. Then also, it is cheaper to construct, since only one surface requires the grinding, that is the coating. And then also, when curved mirrors of a larger diameter are used, then a greater resolving power is obtained. When you talk of a resolving power, you talk about the ability of that instrument to view images to the greatest detail, to have the images viewed to a greater detail, whereby you can clearly or distinctly see the parts of that image. Let's look at the disadvantage of reflecting telescope over refracting telescope. So here the major disadvantage is that the reflecting telescope tarnish easily. They tarnish easily and absorb light, resulting in dull images. Let's also look at the differences between the reflecting telescope and the refracting telescope. Let's look at the differences between the telescopes and microscopes. The differences between the telescopes and the microscopes, So here we had already talked about the differences between the telescopes and the microscopes. but we are going to just summarize those differences. Let's just summarize the differences very fast. So here we have, this side we have telescopes, and then this side we have microscopes. So we can see that telescopes are used to view distant objects, microscopes are used to view near objects. Telescopes are have the objectives with a larger focal length, and then here the objective of the microscope has a smaller focal length. Then telescopes have smaller resolving power, microscopes have a large resolving power. Telescopes, for telescopes, they are either reflecting or refracting, while microscopes are only refracting. They're only refracting. Let's also look at some example here. A distant object subtending 6 times 10 power negative 3 radians is viewed with a reflecting telescope whose objective is a concave mirror of a focal length 15 centimeters, Then they are saying that the reflected light is intercepted by a convex mirror placed 12 centimeters from the pole of the objective, where there is a hole. Good. The image is viewed with a convex lens of focal length 5 centimeters used as a magnifying glass, producing a final image at infinity. Question: draw a ray diagram for this arrangement. Then also we calculate the diameter of the real image that would be formed at the principal focus of the concave mirror. That is, talk of the diameter, that's the height of the image. And then also the diameter of the image formed at the pole of the concave mirror, that is still the height of that image. And then also the angular magnification for the arrangement. So let's begin by looking at the ray diagram. When you look at this question, you find that this is a setup like that of the Cassegrain telescope in normal adjustment. So you're going to just use that ray diagram, and then you're seeing that the intermediate image formed by the concave mirror is going to be at this point, which is a distance 15 centimeters from because this will be the principal focus of the concave mirror, and they have said that the focal length is 15, so that's going to be 15 centimeters from the concave mirror. And if this is 15, and they're saying that the distance between the convex mirror and the concave mirror is going to be 12 centimeters. So that means that from here up to here is 12 centimeters, giving us a balance of 3 centimeters. So the distance from this point up to the convex mirror is 3 centimeters. So that will help us so much in the calculations. Let's begin by looking at this second part, that's part B, Roman 1. They want us to calculate the diameter of the real image that would be formed at the focus of the concave mirror. They want us to get the diameter of this image here. So we're going to let that height be h1, and then we shall let the height of that image, or the diameter of that image, that is the intermediate image formed by the concave mirror, be h1. So if I look at the ray diagram, we shall have this. So we shall have this, and then we can see that the angle subtended, we are calling it theta. So this is the height of the image h1, and that image is formed at the principal focus of the concave mirror. So the distance from h1 up to the concave mirror is 15 centimeter. So now if I want to get this, it means that we are going to let this is a small angle in radians. If you observe that theta is a small angle measured in radians. So it means that theta is approximately equal to tan theta, which is equal to opposite h1 over adjacent, which is 15. So it means that we shall have our theta, which is the 6 times 10 power negative 3, is equal to h1 over 15. And therefore h1 is going to be 15 times 6 times 10 power negative 3, and that will give us 0.0. That will give us 0.09 centimeters. So that will be the height of the image formed at the principal focus of the concave mirror, and that is also the diameter of that real image. Now let's look at the second part of that part B, the Roman numeral 2. That's the diameter of the image formed at the pole of the concave mirror. So they want us to get the image from the diameter of this image here. But remember that that image is formed by the convex mirror. So we're going to consider the action of the convex mirror. And if you consider the action of the convex mirror, we are going to see that, first of all, when you consider the magnification, we are going to let the image formed by this convex mirror, that image, the height of that image should be h2. So it means that the height of the height of the image formed by the concave mirror is h1, and that image formed by the concave mirror acts as the object for the convex mirror. So the image formed by the concave mirror at this point acts as the object for the convex mirror. So it means that the object height for the convex mirror is going to be h1, while the image height is going to be h2. So the magnification is going to be h2 divided by h1, which is also going to be equal to v over u, because you know that linear magnification is given by v over u, or height of image over height of object. But we know the h1, which is 0.09. We know v, the distance from this point up this point, that is from the image formed by the convex mirror and the convex mirror, that distance is 12 centimeters. And then the distance from here up to here, which is the object height, is 3 centimeters. So it means we shall substitute that and shall get our h2 as 0.36 centimeters. So the required diameter, the required height there is 0.3 centimeters, 0.36 centimeters. That is the height of the image formed by the convex mirror at the pole of the concave mirror. Let us also look at the angular magnification for the arrangement. We shall just use the formula. We know that the formula for angular magnification is given by f naught over fe, and we know that f naught is the focal length of the objective, which is 15, and fe is the focal length of the eyepiece, which is 5. So we shall have 15 divided by 5, which will give us 3. So the angular magnification of this arrangement is 3. Yeah. Thank you for your attention. We meet in the next lesson.